Hello. So today we're going to look at some more examples with similar triangles. So the first one that we're going to look at is actually a quite common one, especially when it comes to surveying or looking at large distances and trying to find measurements of things that you can actually see or actually measure. So what do you mean by that? Well, what I mean is, let's say we had this huge canyon out, maybe like the Grand Canyon or something. And we're trying to see how far is it from this point to this point on the canyon. Well, luckily there's a bridge. It's a little far away, but that's okay. There's a bridge over here that we can set up a machine that allows us to measure the distance to a certain point. So this machine measures to this end here and to this end here. And what we see is we get 90 feet and we get 75 feet. Okay? Well, we take that and translate it continuing on to just the endpoints of the bridge. So we get to two endpoints on the bridge. We get 2.5 feet away from the machine and then 3 feet away from the machine. And we see that distance is 4.2 feet. So I redrew that here so that you can kind of see it in a little bit bigger. So the distance from the point of intersection here is 90, and here is 75. From here to here is 3 feet. That's 4.2. That's 2.5 feet. And we're trying to find x because we need to know how far is this canyon from this point to this point. Well, we can use the fact that these two triangles are similar in order to find x. Well, how do I know those two triangles are similar? Well, in order for them to be similar, they have to have congruent angles. Well, because of how this is drawn, if I were to have these two lines here, this bridge would have to be parallel to that distance. And because it's parallel, that means that if I draw a line from one parallel portion to the other, I know then that where that line intersects the parallel line, it's going to be congruent over here. Okay? So some of you may have heard of parallel lines and transversals, and I have there'll be a link to a Khan Academy video about it, kind of detailing this in more detail. Learning about all the how and why behind it is actually kind of cool, but it's not necessary. For many people, they actually kind of can easily visualize this because, hey, if this angle is supposed to intersect this line and I get this angle, when I do the same thing to a line that's supposed to be in the supposed to be parallel to it, has to do the same thing. It makes sense. So because the same line is intersecting similar lines, they're going to have the same angle of intersection. Okay. Well, that means the same thing over here with this guy down here. Okay. Well, what does that leave us in? Well, it actually leaves us something else that is quite common for many people to know. If we take two intersecting lines, this angle and this angle must be congruent. This is called vertical angles. They're called vertical angles, usually one's above the other. They're vertical, depending on your point of view. I'm sure there's some other reasons why people have come up with that name, but that was just the one that I was always told. Now, that means that these two angles have to be congruent. So that means we have all three sets of angles congruent to one another. Therefore, these triangles have to be similar. Well, why aren't they just congruent triangles? Because 90 is definitely not equal to 3. They're not the same. 75 is not the same as 2.5. 4.2 is not the same as x. However, they will be similar. Well, how do I even know that the 90 goes with the 3? Well, 90 is opposite of this angle, and the same angle is down here, and its corresponding side is 3. So the 90 is related to the 3. That also means that 75 is related to the 2.5, and x must be related to 4.2. So 90 goes to the 3, 75 goes to 2.5, and x goes to 4.2. Okay, that's kind of cool that we figured that out. That makes this a lot easier to set up. Do you see the relationship between these sides? Maybe you do automatically, but if you don't, that's okay. We can set up a proportion for this to find the proportionality constant. Well, we know that Well, maybe you automatically know. Well, let's say you didn't know what it is automatically. If we didn't know what it was automatically, we can set up a proportion for just the one that we're looking for, or in general. So in general, we could do what is 90 divided by 3, and we get 30. Well, let's see if we get the same thing. We go 75 divided by 2.5. Oh, we get 30 again. That means when we do x divided by 4.2, we should also get 30. Well, how can we solve for x? Well, we set up this proportionality constant now. We set up this proportion equation using the proportionality constant. So we know that x divided by 4.2 should equal 30. Well, how would you solve for x? Well, we would multiply both sides by 4.2. And then we would see x would have to equal 126. Okay. Now, for the sake of the problem, and for you seeing that, I'm going to erase the top little display of our bridge and our canyon so that we can have a little more room to see that. So if you need to pause the video, go ahead and copy down your information. Okay. So we know that the proportionality constant is 30. So if we had x over 4.2 and it's equal to 30, how would you solve for x? Well, it's division. So the inverse operation of division would be multiplication. So we multiply both sides by 4.2. These divide to 1, and we get x equals 126. All right, so that means the canyon is 126 feet. Okay, and that is how you'll use similar triangles in this example. Now, this is a common one, having parallel lines and having lines or transversals cut between them. These form triangles, as you can see. And when they do, we actually automatically know that these triangles are going to be similar, because this angles has to be the same because they are vertical. And then these angles have to be the same as well because they correspond to one another. All right, so that's an example with similar triangles. We'll look at another one next. See you soon.